the another session of reaction turbine. In this class, we are discussing about some of the problems regarding the reaction turbine. So, going to the first problem, an inward flow reaction turbine has external and internal diameters as 1.08 meter and 0.54 meter. The turbine is running at 200 rpm. The width of the turbine at the inlet is 240 mm and velocity of flow through the runner is constant and is equal to 2.16 meter per second. The guide blades makes an angle of 10 degree to the tangent of the wheel and discharge of at the outlet of the turbine is radial. Draw the inlet and outlet velocity triangles and determine the following. So we need to determine the following 9 things. Okay, the first one is absolute velocity of water at inlet. That means we need to find V1. So here we need to find V1. And next, velocity of whirl at the inlet VW1, relative velocity at inlet VR1, and runner blade angles. Runner blade angles means theta and phi. And width of the runner at the outlet. Width at the inlet is given, so we need to find width at the outlet. Next, we need to find weight of water flowing through the runner. So we need to find weight of water flowing and head at the inlet of the turbine, head at the inlet H, power developed P, and finally we need to find hydraulic efficiency. So first of all, look at to the velocity triangle. So the velocity triangle consists of alpha V1, VR1, VF1. As we look at the inlet of the velocity triangle, inlet side of the velocity triangle, it is very much similar as we discussed in our series of blades. So at the outlet, the water is flowing radially. So since it is a radial outlet, the velocity Vf2 is equal to V2. The absolute velocity of the water at the outlet is radial. Radial, it is at the radial direction. So Vf2 is equal to V2. That means beta is equal to 90 degree. So this is the case. So we need to find the various terms. At the inlet, we need to find V1, VR1, etc. And we need to find the value of theta. So here we need to find value of theta. And at the outlet, we need to find phi, etc. And we need to find the hydraulic efficiency of the turbine. So the given values are internal diameter 1.08 meter, external diameter 1.08 meter, internal diameter 0.54 meter, speed is given as 200 rpm, width at the inlet is given, it is 240 mm, so 0.24 meter, velocity of flow at the inlet is Vf1. So for a radially outlet, so Vf1 is equal to Vf2. So the value is already given there in the question itself. So 2.16 meter per second. Guide blade angle alpha is equal to 10 degree. So the inlet and outlet diameters are given. From the inlet and outlet diameter, we can find U1 and U2. U1 is obtained from the equation pi d and d1 n by 60, and U2 is equal to U2 is the peripheral velocity at the exit. So it is pi d2 n by 60. So the values will be 11.31 meter per second and 5.65 meter per second. The diameter is 1.08 and 0.54. From this values itself, it is defined that the diameter at outlet is double the diameter at the inlet. So next we need to find the absolute velocity of the water at inlet of the runner. So absolute velocity of water at inlet of the runner is V1. V1, we need to find the value V1. So how will you find V1? we know that the value of Vf1 is given. So Vf1 is equal to 2 point Vf1 is given 2.16 meter per second. So we know that Vf1 is the vertical component of V1. Vf1 is the vertical. So Vf1 is the vertical component of V1. So this is Vf1. So we can take it as V1 sin alpha is equal to Vf1. V1 sin alpha. Vf1 is equal to V1 sin alpha. From this equation, V1 is equal to Vf1 divided by sin alpha. So that by substituting the values, you will get the answer as 12.44 meter per second. Next, we need to find the velocity of whirl at the inlet. So Vf1, if Vf1 is the vertical component, Vw1 is equal to the horizontal component. So Vw1 is equal to V1 cos alpha. So V1 already we have find out. It is 12.44 into cos 10 degree. Alpha is 10 degree. So cos 10 degree, and it will give value 12.25 meter per second. Relative velocity at inlet. Next, we need to find relative velocity at inlet. I can go to the inlet velocity triangle. So VR1. So we need to find VR1. So VF1 we already know, and we know the values of VW1 and U1. So from this triangle, so taking this triangle, we know that VR1 is the hypotenuse. VR1 square is equal to this length, which is VW1 minus U1 whole square plus VF1 square. So VR1 is equal to root of VW1 minus U1 whole square plus VF1 square. So from this equation, we can obtain the value of VR1. So VR1 is equal to 2.35 meter per second. Next, we need to find the runner blade angles, that is theta and phi. So theta can be obtained from the equation tan theta. So considering the same equation, same velocity triangle. So this is the triangle. So from this, tan theta is equal to Vf1 divided by Vw1 minus U1. From this equation, we know the value of Vf1, Vw1 and Vu1. From this equation, theta is equal to tan inverse Vf1 divided by Vw1 minus U1. So from this equation, you will get the value of theta. So theta value will be 66.48 degree. So from the outlet velocity triangle. So considering the outlet velocity triangle, so the velocity triangle is, this is the outlet velocity triangle. So taking tan phi, what will get? Tan phi is equal to Vf2 divided by U2. So tan phi, from the equation tan phi. Sorry, here the term is phi. There is a mistake here. So tan phi is equal to Vf2 divided by U2 is equal to 2.16 divided by 5.65 gives 0.382. So phi is equal to tan inverse 0.382 gives 20.9 degree. So we obtained the values of theta and phi. So next, width of the runner at outlet. So we know that from the continuity equation is A1 V1 is equal to A2 V2. So here we can take it as, for reaction turbine, pi D1 into B1 gives area. Vf1 is the velocity of flow at the inlet, is equal to pi D2 B2 into Vf2. So these two values are same, and these two values are same. So the remaining is, sorry, B1 D1 is equal to B2 So we need to find B2, value of B2, width of the blade runner at the outlet is equal to B2 is equal to B1 D1 divided by D2. So D1 into B1 divided by D2 is 1.08 into 0.24 divided by 0.54 gives 0.48 meter. Next, velocity of water flowing per second. Weight of water, sorry, not velocity, weight of water flowing per second. Weight of water is obtained from the equation W into Q. W is the weight density. So W into pi into Q is the discharge. Discharge is area into velocity. Area is pi into D into B1. Velocity is Vf1. So 9.81 into pi into 1.08 into 0.24 into 2.16, which will give the value 17.25 kilonewton per second. So next we are going to find the head at inlet of the turbine. Head at the inlet of the turbine. So we have already derived this equation in the last video. So substituting the values. So we know that the VW2 is 0 here. Since the water is flowing radially at the outlet, the VW2 term is 0. So this term is neglected. So 1 by G into VW1 U1 plus VW2 divided by 2G. So substituting the values, we will get it as 14.36 meter. Next, power developed. Power developed, equation for the power developed is equal to the work done per second. So work done per second is equal to WQ by G into VW1. And if you want to refer these values, you can view my previous videos. So this is the equation for the power developed. So substituting the values. Substituting the values, you will obtain the power developed as 243.6 kilowatt. Next, we need to find the hydraulic efficiency. Hydraulic efficiency is given as VW1 U1 G divided by H. So which is equal to VW1 U1 divided by GH. This is the equation for hydraulic efficiency. So all the values are known. H is obtained from the previous equation. So H is substituted here and all other values are also substituted here, giving the value as 98.35 percentage. So that's all for the first problem. So moving to the second problem. So the second problem is given as in an inward flow reaction turbine, the head on the turbine is 32 meters. So head is already given. So it is given as 32 meter. The external and internal diameter. So external diameter is 1.44 meter and internal diameter is 0.72. That is half of the external diameter. The velocity of flow through the runner is constant and is equal to 3 meter per second. So Vf1 is equal to Vf2 is equal to 3 meter per second. The guide blade angle is 10 degree and the runner vanes are, this is not rigid, it is radial at inlet. Runner vanes are radial at inlet. So replace the term rigid with radial at inlet. If the discharge at outlet is radial, determine the speed. We need to find N, the vane angle at outlet of the runner, and hydraulic efficiency. We need to find the vane angle and hydraulic efficiency. So looking at the velocity triangle, since the runner vanes are radial at the inlet, so here the runner vanes are radial at the inlet. That means what? That means radial at inlet means theta is equal to 90 degrees. So theta value is equal to 90 degree. The significance is that VR1 is equal to VF1. So theta becomes 90 degree and also VW1 is equal to U1 And also it is given that velocity of flow at inlet is equal to velocity of flow at outlet. So Vf1 is equal to Vf2 is equal to 3 meter per second. Head on the turbine is given 32 meter, external diameter 1.44 meter and internal diameter 0.72 meter. So the discharge is a radial. So discharge is radial means we know that Vw2 is equal to 0 here. Vw2 term is not there. Vw2 is equal to 0. V2 is equal to Vf2. So from the given data itself, we can find out the various values of various other terms. So from this equation, we know that Vr1 is equal to 3 meter. V2 is equal to 3 meter. So V2 is equal to Vf2. So V2 is equal to 3 meter. Like that, we have already find out the values of certain terms. Now, speed of the turbine. So, in order to find speed of the turbine, we need to take this equation. U1 is equal to pi and D1 n by 60. So, if we know the values of U1 and D1, then we can find n. N is equal to 60 U divided by pi into D1. So, this is the equation. So, in order to find U, tan alpha. So, from the velocity triangle, so from this triangle, tan alpha is equal to what? Tan alpha is equal to Vf1 divided by U1. Vf1 value is already known and alpha is 10 degree. So from this equation, we can obtain the value of U. So U is equal to 17.01 meter per second. So U1 is equal to pi D1 n by 60. So from this equation, so this is the equation. Substituting the values, you will get the RPM as 225.6 RPM. Next, Vane angle at outlet of the runner. So in order to obtain Vane angle at the outlet of the runner, let us go back to the velocity triangle. Vane angle at the outlet. So the Vane angle at the outlet is phi. Tan phi is equal to Vf2 divided by U2. So will you find U2? U2 is equal to pi D2n by 60. So from this equation you will get the value of U2. So U2 is obtained and it is obtained as 8.505 meter per second from the velocity triangle Vf2. Tan phi is equal to Vf2 by U2. So phi is equal to 19.43 degree. Next, hydraulic efficiency. As we discussed earlier, the high value of hydraulic efficiency is equal to hydraulic efficiency Vw1 U1. For reaction turbine, you can by heart this equation for hydraulic efficiency Vw1 U1 divided by GH. Substituting all the terms are known and you can substitute those values here so that you will get the answer as 92.17%. So that's all for this video.